So, being so familiar with regular languages and regular grammars and whatnot, you may have the following question. All right, regular grammars were fun, but the thing that I really liked about regular languages was being able to draw NFAs and DFAs, right? Because that, for a lot of people, students and faculty, that just seems much more intuitive if you're just drawing it out, right? If you draw it as a machine, it's some sort of an automaton. And so perhaps you have the question, is there a machine that we can use to represent a context-free language, right? I can deal with these grammars, but I'd really like to see a machine. And, I mean, you probably guessed the punchline here. I probably wouldn't have asked the question had there not been one. Yes, there is. The machine is called a pushdown automaton. Now, pushdown automata, right, singular automaton, multiple automata, are actually very, very similar to NFAs. And what is a pushdown automaton? Well, it's essentially an NFA with a stack. So I imagine for most of you this is review, but maybe not for everybody. So a stack is a data structure that has 3 different operations that you can do on it. And what I should say is lots of people have lots of different variations on the interface for a stack with what the built-in functionality of a stack is. These are the operations we're going to use for our class. So if you have a stack, you can push a value onto the stack, you can pop a value off of the stack, or you can do a no-op, which just means do nothing. Now, what does this mean? Well, ignore this picture for a minute. We'll get back to the picture in a minute. The classic stack example that is given to people if you are not familiar with stacks is that of a stack that's found in a dining hall, a stack of dishes. So you can imagine in some dining services or whatever, they have this kind of magical box thing that holds plates. And it's made so that at any given time you can only see a single dinner plate on the very top. And there's some kind of a spring in here, and there's a whole bunch of plates stacked up on top of each other. These are all supposed to be plates, one on top of the other. Whereas this thing down at the bottom is a spring. You did not take this class for my artistic ability. Anyway, and what happens is if you take this top plate, right, and you remove it from the stack, then the spring is weighted so perfectly that it pushes up a little bit and reveals the next plate, so that at any given time there's only one plate visible on the top of this stack of plates. And if you pile a few more plates on top, they will all kind of push, the weight of them will push it down because it's such a perfectly balanced spring, so you only see one plate on top. So if we get rid of all these beautiful drawings for a minute, here's the kind of stack we're going to use in class, this thing. And I'll draw it like this. It sort of looks like a better version of the dining service stack. But this is a stack that has 3 items on it. At the very bottom of the stack there's an X, then there is a B, and then at the top of the stack there's an A. So if I say push some value on this stack, for example, suppose I push another B, then what happens is that B gets added to the top of the stack. And if now I push a C, that C gets added to the top of the stack. And if I say do a no-op, then nothing happens. But if I say pop, what happens is this top value, whatever's the top value on the stack, in this case the C, is returned. It's taken off of the stack and it's returned as the value from the method. So if I do this pop, it's going to return a C, and if I do another pop, it'll return that B. That's essentially a stack. So a PDA, a pushdown automaton, I said, is an NFA, but the NFA, in addition to getting all the content that your standard NFA gets, we also get this bonus stack. And it's amazing how just given a stack, we can suddenly go from only recognizing regular languages to recognizing context-free ones. Okay, so let's start talking about PDAs. And what we're going to do is I'm going to start by just showing you kind of some PDAs that look very much like NFAs and comparing them to the NFAs, and then we'll talk about PDAs that are very different. So here's an NFA, right? This is an NFA. And this NFA accepts the regular expression, or the language of the regular expression C plus Q, right? It accepts a string C and accepts a string Q, right? And when we're talking about this, we might do that sort of zigzag notation where I say I start in, here's my string C. Let's say I start in state 0, and I see a C, and so I traverse this, and I end up in state 1. Right? Or I start in state 0, and then I see a Q, and I end up in state 2. And I missed the part where I say I end up in state 1, and I've used up my whole string, and state 1 is a final state. It's an accept state. So I say, yay, that's in my language. Or state 2 is a final state, right? So I say, yay, I've used up my whole string, and I'm at there, so that's in the language. And let me just erase some of this stuff so I have a little bit more room. And in contrast, if I had the string C, well, let's make it CQQ, right? That's not in my language, right? And how do I know that? Well, I start at state 0, and I can see the C and traverse over to state 1. That's fine. But now I'm stuck. I'm in state 1. I still have to process these two Qs, right? These guys. I don't have anywhere to go, so I fail. Okay? Okay, now here on the right in purple, I have a very similar PDA, and my PDA is going to accept the language A plus B, right? The regular expression of that language. Just it's going to accept an A or it's going to accept a B. Very much like this NFA accepted C plus Q, right? And let me just explain to you this NFA language because it's a little bit weird here, right? Instead of just having a single letter on a transition now, we actually have this sort of fraction thing here, okay? And we also now, of course, you know we have a stack because I was telling you about stacks. I told you PDAs have stacks. And PDAs always start with an X at the bottom of the stack. Before you start your processing, you always have an X at the bottom of the stack. And let me just explain these fraction notation thing here, okay? This says you can take this transition. If you see the letter A, there is an X at the top of your stack. Then you can take the transition. And if you do take the transition, then you got to push a Y onto your stack. So down here it says if you see the letter B and there's an X at the top of your stack, then do a no-op. Then just go across here, but don't change the stack. So let's just look at a couple of examples of what happens if we process some strings on this stack, the purple stack on the right. Okay, so I just put that gray blob there so we can write and have some space. So let's suppose that I have just the string A here. I'm still going to start at state 0. And I look at my transitions on my PDA, and this one says you have to have a B as your next letter. Well, I have an A, so that's no good. But this one says, oh, if you have an A as your next letter and there's an X at the top of the stack, so I check and I say, oh, I have an A as my next letter and an X at the top of the stack, then you can take this over to 1. So I'm going to say, yep, I'm going to go my A, I'm going to end up at state 1. And what does it say? It says you have to push a Y. So after I go to state 1, I'm going to put a Y on top of that X in my stack, okay? And then what you do is you say, have I used up all my letters? Yeah, I have. There was just an A. Am I at an accept state? Yeah, I am. I'm at the state 1. So yay, thumbs up, I win. The string A is in my language, okay? And we can also see that the string B is in my language. Let's just erase some of this stuff. Hang on. All right, let's suppose I had just the string B, right? Well, I started state 0 as usual, right? Because there's my start. And I have a B in my string, and you always start with an X at the top of the stack. So I can take that, I'm at 0 and I have a B, and I can use that B. Oh, look, it says if I have a B and an X at the top of the stack, then I can transition down to 2 and no op, do nothing to the stack. So now I'm going to be at state 2, and I'm not going to change the stack. So now the stack is empty. I mean, sorry, it's not empty, but it just has that X on there, or I guess X is the empty stack symbol. And now I say, oh, I've used up all the letters in my string, and I'm at an accept state. 2 is a double circle, 2 is a final state. So, yep, I guess B is in my string. The string B is in my language. Now, on the other hand, the string, let's make the string ABC is not in my language, because if I start at state 0 and I see an A, and we start with an X on my stack, right? That tells me that I can take this transition here, right? There's an A as my letter, X on my stack, so I can go to 1 and push Y. So I'll go to 1 and I will push a Y. But now I'm stuck, because now I see a B and there's a Y at the top of my stack, and I'm at state 1. But there's no out arrows from here, and I haven't used up all the letters in my stack. So yeah, I'm at a final state, an accept state, but I haven't used up my B and my C yet, so I don't accept, I reject this string. Now this is probably the most important slide you'll see in this deck. And it's just to remind you that just like with an NFA, all you need to do is use up all the letters and end up at a final state, and you're good. With a PDA, you just have to use up all the letters, right? So you have to process your string. Your string has to be completely processed, and you have to be at a final state, an accept state, and then you're good. And it doesn't matter if there's anything left over on the stack. So remember this example. When we had the string A, when we had the string A, and I started at 0, right? I processed the A, I ended up at state 1, and it told me, right? I said I have an A with an X at the top of the stack, so I ended up at state 1. It said push Y. I put a Y up here, and then I said, okay, I'm at state 1. Oh, and I've used up all the letters in my string, and state 1 is a final state. So, yep, the string A is in my language. And it was in my language even though there was still a Y stuck on that stack. I don't care, there's junk still on the stack. I accept. So here's a more formal definition. A string is accepted by a PDA if there is some path from the start state to a final state that consumes all the letters of the string, right? And it starts at the start state and it ends at a final state, right? Final state just means an accept state, right? Otherwise, the string is rejected, and the language of the PDA is just like languages of NFAs. It's the set of all the strings that it accepts. So here's a slightly more complicated PDA. This is a PDA that accepts the string ABC and only ABC. So we start at state 0, and we see the letter A, and of course we have an X at the top of the stack, right? And you look, and state 0 has 2 out transitions. There's this one, but that one requires you to have the letter B and a Y on the stack. Oh, but there's also this one which says you could have an A, right, which I do, and an X on the top of the stack that I do. So let's take this loop. We'll end up back at state 0, but we have to do whatever it says under the fraction thing, so push Y. So we add a Y to my stack, right? And now I'm at state 0, and I see a B, right? And so I look and say, what can I do? Well, I can't do this loop because it wants an A and I have a B, and also it wants an X at the top of the stack, and now I have a Y at the top of the stack. But, oh, look at this. I have a B. If I see the letter B and there's a Y at the top of my stack, look at that. I can take this transition and pop. So I'm going to take this transition to state 1. So I'll end up at state 1, and I will pop. So I will get rid of that Y. So X is back at the only thing on my stack. All right. And now I'm at state 1, and I take a look, and I have a C, and there's an X on the stack at the top of the stack, and oh look, CX no op will get me to 2, so let's do that. So I take the letter C, I go to 2 because I have a C and an X at the top of the stack. I go to 2, I do a no op, so I don't change the stack. And now I'm at state 2. I have used up all the letters in my string, and state 2 is a final state, so I can say yay, accept. Now that wiggle notation gets very old very quickly, and so what we're going to do is we're going to use a different notation that the book gives us. And the book's notation says what you do is you give a series of 3 tuples, of course, where the first one is the state you're at, the second one is what's left of your string to process, and the last one is what's on your stack, where the bottom thing is on the right of the stack. So, for example, if we try and process the string ABC again, so let's see, we start at state 0, and we have the string ABC as the string we want to process, and our stack starts with just an X on it, right? And so we see the letter A is the next letter up, and we have an X on the stack, and so we say, oh, look, I can take this loop. And so it says, all right, well, we did that. We end up at state 0 again, but now we've processed that A, so now we should leave that as an A. That was where we were. Now we just have the string BC, but it said after we take that transition, we needed to push a Y. So we push on the left, so now our stack has YX on it. Right? This is just like the example we did on the previous slide, except I'm kind of writing it horizontally. All right. Now I see a B and there's a Y at the top of the stack. I wish I had more room. So obviously we can take this transition to state 1 and pop. So now I'm at state 1. I have processed the B, so now I just have a C in my letters to process, my string to process, and we're back to, we popped the Y, so now we just have an X on our stack. And now I have a C and an X, right? C is the only letter left in my string, X is the top of the stack, and luckily I can take this, so I end up at state 2 with nothing on, no letters left, lambda, and X on my stack. And I have lambda as my string left over, so I check and I say, is state 2 a final state? Is it an accept state? I look, it's got a double circle, yes. So I say, yay, we accept this string. So ABC is in my language. Now notice that this PDA does not accept the string AAA star, well, does not accept the language AAA star BC. It doesn't accept, for example, let's try the string, where is my pen? Here we go. Let's try the string just AABC, right? So we start at state 0, we're trying to process AABC, and we have an X on our stack to begin with, right? So we start out with an A and an X at the top of the stack, and of course we know we can take this loop and then just push a Y. So we process that first A, and now we are still at state 0, but now our string is just ABC, and we have YX on our stack, right? And now I'm at state 0. I have an A as the next letter to process, and I have a Y at the top of my stack, and I look at my options, and there's no way to get out of state 0. Because this loop says you need the letter A with an X at the top of the stack, but I don't have that. I have a Y at the top of the stack. And this transition out of 0 says you need the letter B and a Y at the top of the stack. Well, I have the Y at the top of the stack, but I don't have a B that I'm processing right now. So this string just loses, right? It's just, no, not in my language. Now, I'm just going to remind you again, a PDA accepts when the string has all been processed, right? You have to get through all the letters, and you're at an accept state. So here's a slight variation on that PDA we've been working with for a little while. This one has a couple of extra transitions. So in addition to the loop where you see an A up next and you have an X at the top of the stack, there's also another loop on 0 where you see an A and there's a Y at the top of the stack. And we've added to this transition another option. Before we had, you see a C and there's an X on the stack, don't do anything. Now we also have, if you see a C and there's a Y on the top of the stack, do nothing. And I'm claiming that this accepts this language, right? You have to have at least one A, but once you've had one A, you can have as many A's as you want after that, and followed by BC. So let's just shrink this a little bit. Hang on. And let's try processing, let's try the string 3A's BC. And we start with an X at the top of the stack, because that's what we always do, and we start at state 0. All right, so I'm processing that first A, and I see an X at the top of the stack, and I have 3 possible transitions I could take. Let's see, I can't take this one because I don't have a B or a Y at the top of the stack for that matter. Can't take this one because I do have the letter A, but I don't have a Y at the top of the stack, right? But I can take our favorite first one, this guy, right? So now I end up still at the state 0. I've processed that first A, so now my string just has 2 A's BC. And when I took that transition, when I took this transition here, it said after you do that, push a Y. So I need to push a Y on the stack. So now my stack reads YX. All right. And now I have an A up next, and there's a Y at the top of my stack. So I am going to, let's see, I have an A up next. Oh, I can't take this one because it's got an X, but oh, look, A up next and a Y at the top of my stack. So take this loopy transition and push Y. And I could have put both of these guys onto a single loop if I could have managed it. I just thought it was getting hard to read, so I put the other loop at the bottom. So I'm going to see an A, Y at the top of the stack. Yep, so I have to push a Y after I take the transition. So now I'm still at state 0. I've processed that A, so now I just have ABC. And now on my stack I have YYX, right? So that would be equivalent to, look, it looks like this in, oops, in stack notation. But we're just going to write it like that because it's easier. Okay, so now I keep going. I see the letter A. I have a Y at the top of the stack, so I can take this transition again and push a Y. I'm going to have to shrink my font a little bit here. Let's see if I can squeeze this up. Hang on. Okay, that was magical. So I'm still at state 0. I've processed that A, so now I just have BC. But when I took this loop, I had to push Y after I was done. So now my stack has 3 Y's and an X. Now I have a B at the top of the stack, and I have the letter B up next and a Y at the top of the stack. So can't take this one, can't take, but look, B and a Y at the top of the stack. And it says after you take this transition, pop. So I am at state 1, process the B. So now I just have C and I pop. So I'm going to pop that thing off the top of the stack, that Y, and I end up with 1, 2 Y's and an X on my stack. And now I'm at state 1. I see the letter C and I have a Y at the top of my stack. And fortunately, now this arrow, I have 2 transitions, right? And this one lets me say C, Y at the top of the stack, do a no-op and get to 2. So I'm going to write down that I am now at state 2. I've used up all the letters in my string. That means I'm almost ready to quit. And I did a no-op, so I go YYX. And so let's look at what we have here. I'm at state 2, and state 2 is a final state. And I have processed all the letters in my string. So I don't care what's on the stack. I win. This is accepted. So the string AAABC is in the language of this PDA. Now, I want to point out that if you have a regular expression that your PDA accepts, you could also do it with an NFA. So I kind of say you don't need to use the stack. That means either you can use a PDA, or sorry, you can use an NFA, or you can just do something like I do here, right? So let's just process this string ABC. And we start at state 0. We have ABC and we have an X on the stack. And I'm going to do this kind of quickly. We have an A is up to process, X at the top of the stack. So we're going to take this transition and we're going to end up at state 1 with BC on the stack, and it said no op, so we just still have our X. And then we see this guy, which it fits, right? We have a B with an X at the top of the stack. And look, it says do a no-op again, right? So now we're going to state 2. We just have to process C, and we have an X at the top of the stack. And then now, oh, look at that. We can take this transition. So we are at state 3. We don't have anything else to process, and there's an X still at the top of the stack. We didn't really use the stack for this, right? It's you know, more or less an NFA, right? If I crossed out that guy and I crossed out these bits and I crossed out these bits, I'd have an NFA, right? So PDAs that accept regular expressions don't have to use the stack, right? And when I say they don't need to use the stack, what I mean is if it's a PDA, it still has to have this whole fraction, but I guess maybe it's they don't need to make use of the stack, right? They don't need to put anything on the stack. They don't need to take anything off of it if they don't want to. But just remember, if you have a PDA, you have to have that fraction notation, and the PDA accepts when you're at an accept state and your full string is processed, and we don't care what's on the stack when you're done, okay? So I'm going to do a few more examples where I show you some NFAs and then I show you some PDAs that are similar, just so that you feel more comfortable with PDAs. First off, let me point out that just like there are a bunch of different NFAs for a particular language, you can also have a bunch of different DFAs, or DFAs for that language for sure, but also PDAs for that language. And you may think that one of these NFAs, which happens to be for the language A star B plus BC, is better than the others, is more intuitive, makes more sense to you, whatever. But I hope that if you look at this, at all 4 of these NFAs, and maybe you want to pause the video, you can see that all of them actually accept A to the A star B plus BC. Now, of those 4 NFAs, the one that people will often complain about the most is this one. And what you want to do is you just want to take a look with this NFA and say, people will say, well, what if my A star B, what if the A star part is just lambda? So then I just have the string B, does this accept that? Because they look at this and they say, oh, well, it looks like it forces you to have an A by having to go from Q0 to Q2. But in fact, if you look, if you just have the letter B, this NFA accepts it fine because it just takes this transition instead. So here's one PDA for A star B plus BC. Again, it's not necessarily the best PDA, but it's very similar to the NFA that I showed you, so I've picked this one. Now, if you look at the 2 of them side by side, what you'll see is that if we just look at the PDA for a minute, all of the instructions on the PDA have a letter, right? A letter that's in the string, and then comma, and then all of them have X over no op. Okay, so this means if there's an X at the top of the stack, which remember is what goes in the stack no matter what, then no op, don't worry about the stack. So this example is actually a super don't worry about the stack example where every single one says don't do anything with the stack and just make sure that there's an X at the top of the stack before you do anything. And of course there's always going to be an X at the top of the stack because we didn't do anything and we start out with the X there. So let's just take a look and do an example on this NFA of a string and then on the PDA on the string, and then I think you'll feel better about what's going on. So for starters, see if you can ignore the PDA, and let's just do the example on this NFA for the string A, B. So if we have the string A, B, then we start at Q0, and we see the letter A, so we process it and we go to Q2, right? So let's get rid of that one, and now we know we're at Q2, right? So maybe we say, this is kind of our notation I think I sometimes use. You say you started at Q0, we saw an A, so now we're at Q2. And then we see another A in our string, right? So we're just going to loop and stay at Q2. So we're going to process that next A and stay at Q2. Sorry, my 2 doesn't look really all that good there. We see another A, and so we're going to loop again and stay at Q2. So we stay at Q2. And then finally we see, let's cross that A off because we've processed it. And then we see the letter B, and the only thing we can do from here, even though it's an NFA, it's a pretty straightforward NFA, is we can jump to Q3. So we use up that B, and we jump to Q3, and we're now done, right? We're at Q3, our string is all used up, and Q3 is a double circle, so we say, hurrah, it's in our language. Now let's do that same example on this PDA down here. Now we have one issue here, which is that little kind of, up, down, up, down, up, down approach that I did with the NFA. That works well with an NFA, it doesn't work so well with a PDA. So what we're going to do is we're going to start this new notation for PDAs, where we're going to say, I'm going to show you what's on the state, what's left over of the string, what I haven't crossed out yet, right? So what state I'm on, what's left over of the string after I make that step, and what is on the stack, just so we can kind of keep track of everything. Because I could, I could try and write it here on the stack or whatever, but it's going to get messy, and this way you can kind of follow an example afterwards. So let me slide this over here a little bit so you can see. So we're looking at the string AAAB. So in our first step, we started state 0, right? The string that we have to process is AAAB. Let's see if I can scooch this over just a little bit. There we go. String I have to process is AAAB, and on the stack is an X. How do I know there's an X on the stack? Because there's always an X on the stack when we start, right? The empty stack is symbolized by having an X. Okay, so we see this first letter A, right? And we look at our NFA and we say, where can I go? And there are two possible options here. One option is if I see the letter B, well, that's not going to work, so forget that one. The other one is if I see the letter A, well, that's good. And I have an X at the top of the stack, well, that's good too, because my stack, if I were to draw my stack, I drew it over in the corner, but now you can't see it, right? But if I were to draw my stack here, right, my stack just has an X on it, and I haven't added anything to it, right? But I also know that because I can look at the notation here, there's an X on my stack. So if I have the letter A and there's an X on my stack, then I'm going to jump on this transition and do a no-op, right? So that means I'm going to end up at state 2 having used up this A. So at this point, I can say, well, now I'm at state 2. The string that I have left to process, this is kind of like after I cross out that A, right? I have AAB, and what's on my stack? Well, I still have an X on my stack because I did a no-op. And now the next letter that I see is an A, and there's an X on my stack. So I look, and this one says, well, if you have a B, and well, that doesn't help me, but I have an A. Oh, look, if I have an A and an X on my stack, then take this loop and do a no-op. So I'm going to stay at 2, having processed that A. So now I'm still at state 2, but since I used up this A, my string is just AB now, and I still have an X on my stack. Okay? And let's see, we're at state 2, and the next thing that we see is an A. So again, we have to take this loop because we see an A, and there's an X on the top of the stack, so we're good. We can take this loop. And so now I stay at state 2, but my string is, I used up the A, so I just have a B. So now I'm at state B, but since I did a no-op, still an X on my stack. I know the stack seems pretty useless because I've just got these no-ops still, but you'll see what happens in a minute that makes it more interesting. Okay? And then well, now I see a B, right? And so I can't take that loop anymore because that loop needs an A. So I see a B. Well, this one looks promising. I got to check what's on the stack. An X. Yeah, so I have an X on the stack. So it says B, X, no op. So I use up that B. I don't change the stack, and I jump to state 3. So now I am at state 3. And there is, let's see, I used up that B, so there's nothing left in my string, just lambda, and I still have an X on my stack. And now what you need to do, if you have lambda in here, in other words, you've used up your string, you need to check and say, is 3 a final state? Because if 3 is a final state, then yes, you win. So, yep, we win, and this string is indeed in our language. Okay, so that was a very easy example on a kind of a very easy PDA that didn't use the stack. And of course, if you have a regular language, which is what we have, right? AAAB is a regular expression, and so that represents a regular language. If you have a regular language, then you can always do it with an NFA, so that means you can do it without a stack. Let's take a look at a slightly more complicated PDA that also recognizes this language. Okay, so here's another PDA that represents A star B plus BC. It looks a lot different. It's not necessarily better or worse. It's just another approach to building a PDA that accepts this language. Notice that I've got a bunch of, I have 4 different transitions here, right? You'd be used to if I'd had ABC or AAA, A, comma, A on a regular PDA, that just means that it actually is a shortcut for 4 arrows here, right? But it's just, we're going to use this one transition arrow to represent all of those transitions. And similarly, we're going to use this single arrow to represent these 3 transitions. And since I couldn't fit them in, I squished that extra one at the bottom. And let me just walk you through a few different examples, and I think when you see the examples, you'll understand what's going on. Okay, so let me pull this up here a little bit. So the first example I want to do is the example that we did previously. I want to do AAAB. So let's see, 1, 2, 3. I don't remember if the other one was 3 A's or 4 A's. Let's just do 3 A's and a B. And we're going to use that same notation. So I'm starting at state 0, of course, and I start with an X on the stack because we always start with an X on the stack. Now, to start out with here, I have, let's see, I have an A that I'm processing in my string, and I have an X at the top of my stack. So here's one transition that I could use for it. Of course, this could be non-deterministic. I might have a bunch of choices, but let's just see. So that this, A is my next letter and X on the stack, that works. I can't use this one because it says you have to have an A on the stack. And I can't use either of these because they say I have to have a B as the next letter. If we look down here, this says I have to have a C as the next letter, so that's no good. These two, however, are free jumps, lambda jumps, right? And before, we could just take them whenever we wanted. Now, we can take this one if we have a B on the stack. Well, I don't have a B at the top of the stack. And this free jump I can only take if I have a Q at the top of the stack. Well, I don't. So I guess the only thing I can use right now is this transition right here. I see an A in my string and I have an X at the top of my stack, which is true over here. So we're going to take this loop. And as we take that loop, what's going to happen is our next 3 tuple will say 0. And of course, this A we're done with, right? So now we have A, B, comma, and we look at the transition we took, and it says after we're done taking the transition, push an A. So we need to put an A onto our stack, and so, if we're using the stack over here, then we just kind of add an A up there. That doesn't look much like an A, does it? Over here, what I'm going to do is I'm going to just write the stack from left to right, everything that's on the stack. So we have an A at the top, and then an X. All right, so let's see. So now we have an A that we have to process, and we have an A at the top of the stack. So let's see. We don't have a C, so we can't use that one. We don't have, we could use a free jump if the stack matches, but here we have a B and here we have a Q, and those don't match, so we have to go look at these guys. Of course, if we can't find anything that works, then we lose. It's not in the language. We have an A and a capital A, right? And I think I said this before, but I like to use the capital letters for pushing and popping off the stack just because it kind of mirrors the terminal or the non-terminals in our grammars when we use grammars, and I kind of like that idea. So these guys have to have B's in the string, so no good. This one has to have X on the stack, so no good. You can see I'm avoiding this one, and of course I'm avoiding this one because this one actually works. So we have an A in our string that's the next to be processed and an A at the top of the stack. So we're going to do this one. We're going to take this loop, process this A, and then at the end we're going to push another A onto the stack. So now if I get a pencil, we're still at state 0. Our string is now just AB that we have yet to process, right? Just like with our NFAs, we use up letters in the string. In an NFA, we would just be crossing it out. But of course, since I have to keep track of the stack, this approach makes a little more sense. So, and remember, we took this transition, so it says we have to push an A when we're done. So now we have AX on our stack. Right? Okay, we have to process an A again, and we have an A at the top of our stack, so we look at everything and we realize we have to do this guy again. So let's do that. So we're going to stay, we're looping still, we're at state 0. Now our string is reduced down to a B and just a B, and of course this says we have to push an A after we take that loop, so we'll push another A. So now we're going to have 3 A's on the stack, followed by an X at the very bottom. Okay, and now it gets a little bit more interesting. We have a B as the next letter up, and we have an A on the stack. None of these guys still work, right? Because that one doesn't match the B. We'd have to have the letter match that B for the first thing to work. These guys are free jumps, so if our letter on the stack matches, we're okay, but of course we have an A on the stack and these don't, so we go back up here, and look, here's one. If you have a B as your letter and an A on the stack, then you can push B and again stay at state 0. So okay, let's do that. So we are at state 0. Now we're down to lambda. We've used up all the letters in our string, and we're going to push a capital B on the stack. So it looks like this. And now, since we have a string that's lambda, we can say, oh, well, is state 0 an accept state? And the answer is no, 0 is not an accept state. So that's not going to work for us. So we have to see, can we keep going to somewhere that might accept? And so we have to see, we have a lambda. We don't have any letters to process, but we have a B on the stack. And if we look, all those have letters you have to process. This you have to process as C. But look, we have 2 free jumps. And one of those free jumps says if you have a B at the top of the stack, you can take this jump and do a no-op. Now, free jumps don't have to have a no-op, but this one does. So what we're going to do is we are going to take that free jump and the no-op. So we end up at state 1. So we end up at state 1. We didn't process anything because we took a freebie jump, and it was a no-op, so that tells us this is still on our stack, right? So over here, our stack actually now has 1, 2, 3 A's and a B above that X, right? So that's the way the stack looks. And at this point, we look at the fact that, you know, again, we have a lambda in our string, so we can check to see whether the state we're currently at is an accept state. And sure enough, 1 has double circles, so it's a final state for our PDA. So we say, yep, the string AAAB is in our language, right? So AAAB is in an element of our language. Okay? So there's one good example. Now, let me clean this up and we'll do another example. Okay, now let's try processing the string BB, which is not in our language, so we sure as heck hope it isn't actually accepted. So of course we're going to start at state 0. Our string is BB, and we have an X on our stack because we always start with X on our empty stack. And now let's see, we have a B and an X on our stack, so none of the free jumps let us jump with an X. This has to have a Q and it needs a C anyway. Here's our only B ones. Oh look, BX push Q. Okay, And I can't remember if I said this or not now, but I made it push Q here just because I want you to know that the letters don't necessarily have to match up. So what we're going to do is we are going to say, okay, I'm taking that loop and I'm so say it's 0, and I now have a B left in my string because I processed that first B, but now I have, instead of just an X, because, here we go, because this thing said I have to push Q after I take the transition, now I have to push Q onto my stack. So now my stack has a Q and then an X, okay? And now we take a look and we have another B, and let's look at all the possible transitions we could take with a B. Well, this one says a B, but you have to have an X, and we don't. We have a Q at the top of the stack. This one says a B, but you have to have an A at the top of the stack, and again, we have a Q at the top of the stack, so that's no good. This one is requiring a C, so that's no good. This one is a lambda and requires a B at the top of the stack, so that doesn't work. Oh, look, here's a free jump that says you can take this free jump whenever you want as long as you have a Q at the top of the stack. Okay, so let's take this free jump because I don't see anything else we could do, right? Sometimes there's more than one option on a PDA, but not in this case. So we will take the jump to 1. So we're going to be at state 1. We took a lambda jump, so we didn't use up that B. It was just a free jump. And at the end of doing that jump, it says that we're supposed to do a no-op. So we just leave the stack alone. So our stack still has QX on it. Now, we are at state 1. And if you look at this, there's nowhere else for us to go, right? So if we get here and the string is empty, we don't care what's on the stack when we get to an accept state, right? But if we're here and the string is empty, then we'd say, yes, it's in our language. But we still have stuff to process and we don't have any way to process it. And there's nowhere else we could have gone. So in this case, we're going to say, nope, not in our language. So we're going to say, you know, the string BB is not in the language. What do we got? Well, we're still using regular expressions, so I can just write it like that. A star B plus BC. Okay? Let's do another example. Why don't we just look at the single B for a minute? So if we just have the string B, then we start at state 0. We have X on our stack. And I'm going to go do this a little bit more quickly, but if you look at this, none of these guys work. These two don't work. This one doesn't work. Here's the only one that works, right? We have a B letter to process and an X on our stack. So we're going to take this loop and then push a Q. So we have we're taking the loop, so we're still at state 0. We're using up that B, so now our string is just lambda, and we're pushing a Q, so now our stack is QX. And now we look and we say, oh, look, I have the lambda, but I'm not in an accept state, so that doesn't get me anything. But we can still take this free jump, right? This is a free jump you can take as long as there's a Q at the top of the stack. And we have a Q at the top of the stack, so we're good. So we're going to take the free jump to 1. So we're going to say we have 1. Our string is still lambda, and since that free jump told us we did a no-op, my stack is still QX. And again, now I look and I say, oh, look, I have the string lambda. I've used up all the letters in my string. And I'm at state 1, which is an accept state, so hooray, that's in my language. So B by itself is in my language, which makes sense, right? Because my language includes A star B, which means we could have 0 A's and just a B. So we wanted this to work, so that's good. So we might want to just write B is in the language, and maybe I'll write the language another way, right? So it's A to the N B such that N is in the natural numbers, and it is a set that's unioned with the set that just contains the string BC. Okay, so all good. Let's do one more example with this. Okay, so let's just try and make sure that the string BC is in the language, because we want that to be in the language, right? So we started state 0, we have BC, and our stack starts as the empty stack, which is just the letter X. And if we look at our options here, the only one that we can take is this one, because we have a B as our letter and an X at the top of the stack. So we're going to take this thing that says you have a B letter and an X at the top of the stack, and we're going to push Q. So we end up, and it's a loop, so we stay at 1. We have the letter C, and now our stack has QX on it like before. And now let's see if we look. Now we have a C with a Q at the top of the stack, and check it out. We could take either this guy, which is a C with a Q at the top of the stack, or we could in fact try this one, free jump with a Q at the top of the stack. So we have two options here. Let's try this one first, just for fun. It's not actually going to buy us anything, but we can try. So what we're going to do is, I'm just going to kind of branch out here and say there's two different options. I guess this is a non-deterministic PDA. So in the first case, if I take the transition to state 1, then I'm not processing that C, right? It's just a lambda jump, a free jump. So I'm going to take the transition to state 1. I still have, my string is still C, and this says that I don't do anything with my stack, so it's a no op. So that, oh sorry, yeah, this one. So it says it's a no op, so I'm just going to leave the stack alone. So that's one option of where I could end up. The other option is, instead, if I say I see a C, so I'm going to take this C with a Q at the top of the stack, right? C, Q at the top of the stack, and I'm going to transition using this to 1, but this transition uses up that letter C, and do a no op. So in this case, I end up doing, let's see, I end up at state 1 also, but now I have lambda as my string, and it was a no op, so I still have a QX. So now there's two possibilities, right? Just like with an NFA, there might be two possibilities, and you have to magically, remember magic sparkle dust? I don't know, did I talk about magic sparkle dust? But you have to magically somehow figure out which one works, right? Do any of these paths work? And of course, in a more complicated example, you might have a bunch of possibilities here and a bunch of possibilities here. And as long as you can find one path through this PDA that ends up with the empty string at the end, and you're at an accept state, you're okay. Now, this guy over here is at state 1, which is an accept state, but the string is not empty and there's nowhere else we can go. So this particular possibility, as it were, dies out, right? This one doesn't work anymore. On the other hand, this one is fantastic because we have the empty string and we're at a string that is an accept state. So we know, therefore, that BC is in our language. So notice that we've still never had to do a pop, right? We just haven't seen any examples where we've had to do a pop before. I could have stuffed some pops into that one and they would have been okay, but they wouldn't really have helped us any. And the reason that we haven't had to do that yet is because all of our examples have been regular languages, right? The examples that I've shown you, or the example that I showed you so far, is a regular language. So let's go back to our classic non-regular language example, A to the N, B to the N. So here's a PDA that accepts the language A to the N, B to the N, as long as N is in the natural numbers, so N greater than or equal to 0. And let's just do an example to see what's going on here. Maybe a couple of examples. Let's see. All right. And remember, we always start with X on the bottom of the stack. So let's try the string A, B, B. Okay, that's in the language, right? And we're going to start at state 0, and the stack is going to have an X. And then we process that first A, and we have an X on the stack. So we have two options. One option is we take this path down to state 2, right? Because we have an X on the stack and a free jump. And the other option is this loop here. If you look at this, that's the only one you can do. Well, those are the only two. So let's split this off, and we'll say if we take the first thing and we go to state 2, then we still have our entire string, AABB, and an X on the stack, because it was a no-op at the bottom of state 2, right? Or at the bottom of the transition, right? This says no-op here. Okay. So that's one option, and the other option is we can take this guy, stay at state 0, and push a Y. So in that case, we will have processed, here, let me just move this down here a little bit. Actually, there you go. In that case, we will be at state 0 still. We'll have shrunk our string. Our string will have used, sorry, the first A up. And our stack will now have a Y at the front of it. Ooh, let's try again, right? So we have our stack has Y and then X, okay? And now we say, okay, now if I am at state 2 with an A and an X, oh, there's nothing I can do out of there, so this one's no good. But if I'm at state 0, right, because that one was no good because I wasn't done with my string yet. I hadn't used up my string. If we look at this other situation where at state 0, we have an A to process and a Y at the top of our stack. Well, look here. We have an A to process and a Y. So we can just do that and stay at state 0 and push Y. So we're at state 0. We used up that A, and we're going to push another Y. So now we have YYX on our stack. And we're actually using the Y's to keep track of how many A's, how many lowercase a's we've seen. So now we get to the point where we have a 0 on our stack. Sorry, we're at state 0. We have YYX on our stack, and we're processing a B. So we're processing B, and we have a Y at the top of our stack. Okay? So can't take this free jump because it expects an X, right? Couldn't do that for a while. But here we go, B, Y, and it says pop. So if we see a B, which we do, and there's a Y at the top of our stack, then we can do a pop. So what we're going to have is we're going to say, all right, well, now I'm moving to state 1. I am using up that first B, and I'm going to pop the Y off my stack. Well, I'm going to pop my stack, which takes the top thing off, which means now I just have YX on my stack. Okay, let's see what's next. So I'm at state 1. I have a B and a Y. So I'm here. Oh, look. I can't take this guy because even though it's a free jump, it needs an X on the top of my stack, but this loop works. So BY pop. So basically we're matching up all the B's with all the A's that we've seen. So I have BY pop. So I'm still at state 1. I used up that B. I have lambda, and I'm going to pop. So I pop the top thing off, which happens to be this Y. So I end up with X. Now I have lambda as my string, but state 1 is not an accept state yet, so I have to keep seeing if there's anything else I can do. And look here, now that I have X at the top of my stack, I can take a free jump, not just because I have a lambda here, but because this just means free jump if you have an X on your stack. So I can go from 1 to 2 on my free jump, and I end up at 2, and it says to do a no-op. So I'm going to be at state 2 with a lambda and X on my stack. And now I check again because I have the empty string here, and I say, oh, look, at state 2 is an accept state, so my string AABB is in my language. Thank goodness for that. Now we're going to try, why don't we try and do it again, and this time let's try a string that has 1 A and 2 B's, which is not in the language. Okay, so if we have the string that has 1 A and 2 B's, and we start at state 0, and we start with X on our stack, and initially I have the symbol A with an X at the top of my stack. So I have two options. I can take this one, right, because it's a free jump as long as you have an X on your stack, or I can do this loop and push a Y. But that, I think, is the only stuff I can do. So let's try those two options. Again, that first one isn't going to work, but, you know, what the heck, we have to try it. So I'm going to end up in that first case at 2. It was a free jump, so I didn't use up any of my symbols, and it says no op, so I have an X on my stack. In contrast, if I take that loop, then I'm still at 0. I've used up that first A, and it says push a Y, so now my stack has YX. And now, of course, I have to look at each of these and say, is there a way for me to continue, or does it get accepted and not accepted because there's still a string there, right? Even though I'm at state 2, not accepted because it has to be lambda for me to accept it. Over here, I'm in state 0. 0 isn't even a double circle, isn't even an accept state. It's not a final state, so forget that. From state 2, I can't go anywhere. There's no out arrows, so this is useless. And this one, I have a B, and I see a Y at the top of the stack, and I'm in state 0. And I can't do any of my loops, but I could take this BY pop, right? So let's do that. So this one was useless. This guy, we can go to state 1. We'll use up that first B, and it said, if you see a B and there's a Y at the top of the stack and you take this transition, then you are supposed to pop. So let's pop our stack. And now we just have an X on our stack, right? So notice we just pushed one Y this time because we're sort of using the stack to count how many A's we've seen. So at this point, we're at state 1. We have a B as our letter to still process, and we have an X at the top of the stack. We can't do this BY pop loop because there's no more Y's on the stack, right? We have an X at the top of the stack. We can do this lambda X free jump thing here. In fact, that's the only thing we can do, so we might as well try. So it's going to take us to state 2. Because it's a free jump, we don't use up any letters. And now, let's see. Oh, now we're at state 2. And it said we should do a no-op, so we leave X alone. And now there's nowhere we can go, right? We're sort of stuck. And well, state 2 might be a final state, but we still have a letter in our string here, right? So that still needs to be processed. So we say, oh, look, this language ABB is, sorry, the string ABB is not in our language. So what I'm going to do is I am going to show you this PDA again, a little bit bigger. Let's see if I can move it over. All right. And I'm just going to suggest that you should take a look at this example and try and do it a couple times and make sure that it all works for you. Try some other letters and some other strings and make sure that strings that should be in there are in there, strings that should not be in there are not in there. And, you know, if you try the string lambda, which is in this language, right, then what's going to happen is you'll see why we have this 0 to 2 thing, right? Now, one last thing I want to make totally clear is that a lambda jump in a PDA is just like a free jump in an NFA, except you need to check the stack. All right, so here's a PDA that I've given you that actually we're still accepting regular expressions, but this accepts this language. It accepts the string ABC, and it also accepts the string C. So let's just trace both of those and see what happens. All right, so for ABC, we're going to start at state 0. My string is ABC, X is on the stack, right? And I take this transition, C and A, and there's an X top of the stack, push Y. So I end up at state 1 with BC on the stack, and sorry, BC is my string and YX on my stack. And then so I have a B and a Y at the top of my stack, so I can take that next transition. So I end up at state 2 with C because I processed the B, and it said to pop, so now I just have X on the stack. And then the transition from 2 to 3 works, right? It says if I see a C and there's an X on the top of the stack, yep, then I can push Q. So I end up at state 3. I've used up all my letters, and there is a QX on the stack, but I don't care because I've used up all my letters and I am at a state that is a final state that's an accept state. So I say, check it out, the string ABC is in my language. Now let's just try and trace how the string C works here. Let me clean this up. Now let's start again, and this time let's assume we're at state 0, and all we have as our string is C, and of course we start with X on the stack. So we look, and we have a C, and there is an X at the top of the stack. And we look, and obviously this transition here doesn't work because we don't have an A. And this other transition here, I'm sorry, I put the label down there because I couldn't fit it as easily anywhere else. But this transition has a lambda and X, and this lambda means like free jump, right? So at any time if you feel like it, as long as you have an X at the top of the stack, you can take this jump. So right now, I'm looking, and I have a, I'm at state 0, I have a C on the stack, I have an X at the top of the stack, and I have a C as my next letter, but I feel like taking this transition now. Totally fine, if I take a lambda jump, I don't process this letter. So now, I am, let's see, I'm at state 2, right? I still have the letter C to process, and I didn't do anything because it said to do a no op, so I still have an X on my stack, right? And now I keep going, and it says, oh look, if you see a C and there's an X at the top of the stack, push Q. Well, I have a C, X at the top of the stack, so I'm going to go to state 3 and push a Q. So I'm at state 3, I have lambda, I've used up everything on here, and my stack now has QX, but I'm at the final state, so I accept it. Now, one last thing, let me just clean this up. Just like with NFAs, you can have non-determinism. With PDAs, you can have non-determinism too, right? And so really, when I showed you the path for that, first string, right? We started 0, we see ABC, and there's an X on the stack. In fact, I only showed you half the possibilities, right? Because really, if you were processing this, or in JFlap, for example, what you would say is, okay, well, I have an A and there's an X at the top of the stack. So what transitions can I take? Well, this one has A and X, and that's fine, and then I would push Y. But here's a free jump that also uses X. So this actually says, well, there's 2 paths. One is I end up at 1 with BC in my string left over to process, and you push Y, so YX on my stack. And the other option is I take this bottom loop, and then I end up at state 2, and I haven't processed anything, so I still have ABC, and it said no op, so I have X on my stack still. And then I say, all right, well, if I'm at state 1 and I see BC, YX, I can keep going, so I can end up at state 2 with a C, and I had to pop, so X on my stack. Or if I were taking the second path here, I was at state 2 and I had ABC, and I say, oh, look, I'm at state 2. A is next, and I have an X on the stack. Well, I do have an X on the stack, but the only thing I can do here is if I have a C, so it kind of dies. And this other one says, okay, well, I'm at state 2. I have a C and an X, so I can go to state 3. Now I have lambda, and it said push Q, so I have QX, and I'm at state 3, which is a final state, and I have a lambda in my string, so I say yes to ABC. The big point of this slide, again, is to tell you if you have a lambda as the first thing in your sort of fraction guy here, so if there's a lambda there, then that means as long as the top of the stack matches, you can take the transition and do whatever it says. Of course, we love our tuples. I've tried to color code this, right? This is so you can also represent an edge as a 5 tuple. So if we look, for example, at this red transition label here. We know that to go from 0 to 2, you can go to 0 to 2 on a lambda if you see an x at the top of the stack, and what you should do is a no-op. And this is saying, look, we start at 0, we're going to 2, lambda x no-op, right? So the green is staying at 0, right? If you start at 0, end at 0, you have the letter A, you see an x, you should push a y. For this kind of light blue, again from 0 to 0, if you see a 0, if you are at state 0, you see an A and a y at the top of the stack, you should push a y and then continue to state 0. This one looks like that, and I'm just asking you, what should the 5 tuple be for the last two here? So let's do this first 5 tuple. Well, the first one here, this one is what I'm working on. You're starting at state 1, you are ending at state 1, and you see B, there's a y at the top of the stack, then you pop. For this other transition here, let's do it in a different color, right? You are starting at state 1, you are ending at state 2. It's a free jump, a lambda, but you have to see an x there, and you do a no-op. So another definition for you, this is kind of a definition of do I have to use magic? If a PDA is deterministic, right, then there's at most one move possible from every state. So you don't have to take a magic jump ever, use magic to guess which path to follow. It's always determined. It's deterministic. And if a PDA is not deterministic, then it's called non-deterministic. So here's my question for you. Take a look at the PDA in this image and tell me, is this PDA deterministic or non-deterministic? Right? Is there any state that has two possible moves where you're going to leave the state where you could have the same combination to do so? And the answer is it's actually non-deterministic, because if x is at the top of the stack, right, and A is the next letter, there's two choices. There's this one, which looks obvious if you're at state 0, of course, right? We're talking about from state 0. There are two choices from state 0. If you see an A and X is at the top of the stack, you could take this transition. But you could also say, oh, I'm going to do a free jump now because there's an X at the top of the stack, and I just won't process my A this time. So this PDA that I'm showing you here is non-deterministic, right? Because there are two possible options from at least one of the states. In this case, from state 0, there are two possible options. Now, one nice trick, if you do write out your 5 tuples, is it's pretty easy to tell if a PDA is non-deterministic just by looking at the 5 tuples. So, if either of these two things are true, it's non-deterministic. So, if you've got two 5 tuples that have the same first 3 components, then it's non-deterministic, right? And that makes sense because the first component is where you're starting, right? Let's look at this one for a second. Let's just look at the second line for 1 second, then we'll go back to the first line. So right here, this 0AX push Y, right, that represents this guy here, right? Let me maybe circle both of them. Okay, so this thing here is the 5 tuple for this particular transition from 0 to 0. And if I have another transition that starts at state 0 that sees the letter A, that happens if you see the letter A and there's an X at the top of the stack, that would make it non-deterministic, right? If I looked through my list of 5 tuples and one of them had the same 3 things at the beginning, it would be non-deterministic. But because of these free jumps, there's one other option, which is if they have the same first and third component, and one of the 5 tuples has lambda as the second component. And so that's what's going on here between these two, right? If we look, remember we said that from state 0, there's two options if you see the letter A and you have an X on the top of the stack, right? And we can see that here because since we do have a lambda in the second position, if we have any two 5 tuples that have the first and third thing the same, then we say again it's non-deterministic.